Hi, and welcome to the notes on animal population dynamics. Today we're going to talk about how animals and species grow over time. We've already talked about how humans grow over time in during first semester, and those type of population dynamics are different. Humans have very different growth rates depending on a lot of different factors, like where you are from, where you live, type of resources available to you, if you're a developed country or a developing country, and those dynamics are complex. There are growth rates that are dependent upon religion. There are growth rates dependent upon cultures, and there all kinds of different things. The good thing about animals and animal population dynamics is that they are pretty consistent. So, depending on the type of animal, they all grow at pretty much the same rate. And so, we're going to look at how those things, how different animals grow in their populations, and that ultimately will lead to why we conserve species and why we protect certain species versus other species. Why are we not trying to protect all animals? So there's a reason to that, and so people who do this kind of stuff, they study how populations are changing over time, and that helps with protecting them. And so we're going to look at those today. So first of all, we need to understand how populations grow, how all animal populations grow. And they grow through what is called the logistical growth model. It's an S type of curve. It looks like an S, where populations generally will start off growing fairly slowly, and then they will eventually start to grow exponentially at a certain point in time where there are still tons of resources, there are still tons of food, tons of water, tons of shelter, not enough prey, and they grow pretty freely, able to grow at their own rate, which is generally exponential. And then at some point, everything starts to catch up. Food becomes less and less available, space becomes less and less available. There starts to become more and more prey. Maybe disease comes in. And there are a lot of these things that will start to uh, push the species to slower growth and ultimately a stable growth pattern. And we'll talk about those things. We call them resistance factors, but ultimately species always sort of uh, get to what is called their carrying capacity. So the amount of animals that an ecosystem can support. And so at first you have more resources than animals, and so they can grow very quickly. But then you get to a point where the resources and the animals generally match, and so you start to see that growth slow. In a perfect world and under perfect conditions where there are unlimited, infinite space, infinite water, infinite food, and no predators, they would literally grow exponential forever. But that doesn't happen. And you can see here in this red line, the species without any sort of resistance, and we call that biotic potential, would be exponential. It would grow forever. But like I said, that doesn't happen. Things come in, those resistance factors, which we'll talk about in just a second, come in and they help regulate that population. It could be predators, it could be disease, it could be lots of things, food, resources, water, that kind of thing. But ultimately, they will curve and then level off at some point, which we would call their carrying capacity. Now, like humans, like I said, behave differently. Humans, for a multitude of reasons, have somehow blown right through their carrying capacity, and nobody even knows what their carrying capacity is. There are estimates that it's around 11 or 12 billion, but we don't really know. We thought we were going to reach our carrying capacity a long time ago, but then technology and advances in technology and farming and medicine allowed us to live longer. It allowed us to live healthier. It allowed us to grow more food on the same plot of land, and so we could feed more people. So a lot of things have led to us being able to raise our carrying capacity, but unfortunately, other animals cannot do that. So let's look at some of those resistance factors. So here are the resistance factors. There are natural and then there are human caused. Natural resistance factors like food and water and shelter and disease, those things have always been around and help regulate populations. Climate change over the course of thousands of years that would, regulate populations. And then a big one is predation. So predators ultimately would be in charge of regulating populations. Um, but once humans came around, we started adding our own um, resistance factors. The biggest one has been habitat destruction. Humans ourselves don't take up a lot of space, but the things that we need and want and use, those things take up a lot of space to make. Things like all of our food and all of our meat and all of the mines to mine out materials and manufacture, those things take up a lot of space. And when we take up more space, that just means that there's less space for animals. And that comes back to those food, water, shelter. So less space for animals means that less animals can live there. And so we've driven a lot of these species to extinction just by destroying their habitats. Another big one is hunting and poaching. Now, it's not wrong to hunt. We've been hunting for thousands of years. The difference is that before we were hunting out of necessity. We needed the meat to eat. We needed the the fur or the hide to make as blankets to stay warm or to provide shelter. Now we still do hunt for food, but we also hunt for fun. And so here's a picture of this hunter here and poacher in front of a rhino. Many of the rhinos are endangered, and this picture obviously was taken a long time ago, but this many of our poaching has been for things that we don't necessarily need but want. So, a lot of the fur comes from lions, tigers, cheetahs. Those things, they get hunted, and we don't eat those things. We don't eat the rhino. We don't eat an elephant, but we shoot them, for their horns, or we shoot them for their tusks. We shoot them just for fun. There are people that pay money to just go out and shoot animals for fun. And unfortunately, those type of animals, especially like elephants and rhinos, they just don't grow very quickly. They don't have lots of babies, and so they can't replicate faster than we are, or as fast as we're killing them off. And so their numbers begin to shrink. And it just takes so long for those species to come back that, we're driving those species to extinction. Human-made climate change has been way faster than the normal rates of climate change. Climates change over thousands to tens of thousands of years. We're doing it in a few hundred years. And so we're seeing rapid changes in the Earth's oceans, in the Earth's atmosphere. This is a picture up here on the right is coral bleaching. And that in itself also destroys habitats because the corals are no longer living and then providing resources for all the fish that live there. And so you ultimately have habitat loss that way too. And of course, we're polluting our air and water, which makes places unlivable for a lot of aquatic life as well. The species fall into two types of categories, and it really just depends on how they grow. So the first one is R-selected species. R-selected species, the reason why they're called R-selected species is because their growth rates are tied to exponential growth. And if you've dealt with exponential growth equations, R is that growth factor. And so being that it's tied to exponential equations means that R-selected species generally grow really, really fast. Their numbers increase very, very quickly. So things like bacteria or fish or rabbits or bugs, those things have lots of offspring. They have lots of them, lots of, uh, you know, they give birth a lot of times. And when they do, there's a lot of them, and they reach maturity very, very quickly. They don't live very long. They're generally small. And the reason why they have a growth pattern like that is because they are killed off so quickly. You can't really have like a bug, can't have just one offspring. Those bugs wouldn't survive. And so they have evolved to reproduce very quickly to accommodate for the how fast they die. And that's the survivorship. And we'll talk about that a little bit later. Um, Our selected species also don't provide care for their young. They generally will lay their eggs or have babies and then just like leave. So, turtles, sea turtles will do that. A lot of bugs will just lay their eggs and then leave. Fish will do that. Um, and so that's another characteristic of our selected species as well. Now, K-selected, which humans belong to, they live long lives. And when they have babies, they don't have very many of them over their lifetime. They are pregnant for really long. That's that long gestation period. They care for their young a really long time. Whereas our selected species just like lay eggs and they just peace out. K-selected species often will have offspring and then put a lot of time and effort into raising them. And that's a huge difference. And that really increases the survival rate of babies who have parental care. Um, they also are generally larger. So, like your elephants, your sharks or whales, humans, even trees fall into that same category. And they have a higher survivorship. I mean, like higher on the spectrum. One is the highest, three is the lowest, because they generally don't die very quickly, at least the vast majority of them. And so the growth patterns look very different on a graph. And so we can look at those growth patterns here, and you can see that because our selected species grow so quickly, they often overshoot their carrying capacity, and then go, oh my gosh, we got all these people here, and like, where's all the food? And then they don't have enough food for all those animals, and then they end up dying off, and then shooting back up and dying off. And so this pattern of oscillating back and forth on the carrying capacity is very typical of our selected species. And then you have K-selected species, which K stands for carrying capacity. So the reason why they're called K-selected species is because those populations generally grow very slowly, and then as they approach their carrying capacity, they kind of just hover around there. And that's why they're called K-selected species. But the growth patterns could not be more different. I was talking about survivorship. So here's survivorship again. The type 1 is the highest level of survivorship. That means that most of your species will survive. So this is the percent of survival rate of a species over time. So you can see that type 1, like humans or large mammals like elephants or something like that, they live really, really long lives. Most of them really live really long lives. And then they get to a point where they sort of succumb to disease or something like that. And ultimately die of old age over here. And that's in stark contrast to um, animals that are in type 3 survivorship, where you can see that a super high percentage of them die very, very early in their life. So this is like bugs and stuff like that, which bugs are eaten by everything. They're eaten by, frogs and amphibians and reptiles, and they're eaten by birds and smashed by humans and, killed by pesticides. Lots and lots and lots of bugs die very early, and very few of them make it to older ages within their expected lifespan. You think about a fly. I mean, you rarely see a fly die of old age. Like just, oftentimes it's killed by something. And then there's type 2. You don't really need to know type 2 for this class and for the test, but type 2 would be a type of species that has a sort of consistent death rate throughout its life. And generally, those animals fall into middle-sized animals that aren't going to be killed a ton when they're young, but they are killed throughout their lifetime by either predators or by cars or hunting. And so, like a bunny would fall in there. But the questions that pertain to survivorship on the test will be like really focused on type 1 and type 3. The other thing that can cause growth rates to decline in an ecosystem are invasive species. So sometimes when ecosystems become under stress, you can get a lack of food, a lack of water, a lack of resources or space. And that is when species can come into an environment that is under stress where they have an advantage over the other species. They come in and they can survive in less water, they can survive in hotter temperatures or colder temperatures or more salty, conditions or low pH or high pH. These species come in when an ecosystem is under stress, and they can outcompete the native species who are already stressed out in their ecosystem and push those species to extinction or drive them out of those ecosystems. And that's why they call them invasive species, because they come in and actually do harm to the species in the ecosystem. Not like literally, they're not like, punching the other animals, but like they are causing a negative impact on the native species. Now, that's different from what's called exotic species. Exotic species are also foreign animals that come into an environment or are released into an environment, and but they don't cause a negative impact. For example, like if I owned a parrot, and I accidentally let my parrot out the back door, and that parrot flew off, and I never saw the parrot again, that parrot is not going to outcompete native birds to survive. Parrots are tropical animals, and that parrot will likely die because it can't eat anything here, and it doesn't know how to survive in this ecosystem, and so it's not going to become invasive. So we call those exotic species. They are also animals that come into an ecosystem but don't cause any harm. The last thing, and just on kind of piggyback on invasive species, most of those invasive species are what we call generalists. They can live in a wide range of areas, in a wide range of temperatures or conditions, or eat a wide range of foods. And so generalists oftentimes are your invasive species, and they're less likely to go to extinction. And so the perfect example of these things are your raccoon and your panda. A raccoon, well, we had raccoons in Phoenix, we have raccoons here, there's raccoons in Alaska. Raccoons live everywhere and they eat anything. I mean, they literally eat trash. So they can survive in a wide range of areas. So they are likely not to cause they're not likely to become extinct just because they can survive in so many different conditions. Whereas the panda is like the quintessential specialist in that it only eats one type of food and it only lives in one area in China. And so if that ecosystem becomes under stress or changes, maybe there's a loss in bamboo, or their ecosystem gets too warm or too dry, um, you can drive the panda to extinction. That's ultimately what has happened. Habitat loss and climate change has led to the pandas being put on the endangered species list. And part of it is really to do just because of its habits. It doesn't eat lots of things and it doesn't live in a lot of places, so you can't put it anywhere. And so these are far more prone to extinction, specialists are, compared to generalists. And those are the notes on uh, animal population dynamics. Okay. And so, thank you.